Okay, so this is question number 2 of the magnetic fields homework booklet. So part A of question number 2, we are told that the equation F equals BIL, where the symbols have their usual meanings, gives the magnetic force that acts on the conductor in a magnetic field. We're asked to give the unit of each of these quantities, the unit of F and B and I and L. So F is the force, which is the unit for that is the Newton. B is the magnetic flux density, and the unit for that is the Tesla. I is the current, and the unit for that is the ampere, not just amp, so you've got to write the whole thing, ampere. And L is the length of the thing, and so that's obviously measured in meters. And we're then asked to state the condition under which this equation applies. Well, the current has to be perpendicular to the magnetic flux density. So this thing gets you 1 mark, this thing gets you your 2nd mark. So we're then, in part B, we're then given this diagram, and it shows this horizontal copper bar of 25 millimeters by 25 millimeters and a square cross section. So in other words, this part is a square prism, and it's got a length of L. We don't know what L is, we're simply told it's a length of L, and it carries a current of 65 amps. So we're asked to calculate the minimum value of the flux density for the magnetic field in which this bar should be placed if its weight is going to be supported by the magnetic force that acts upon it. So in other words, if the weight is downwards, the magnetic force is going to be upwards. We're told the density of copper is 8.9 times 10 to the 3 kilograms per meters cubed. So if we're going to do this, what we really need to do is we need to know the weight of the thing downwards, really, because that's going to be equal to the magnetic force upwards in order for the resultant force overall to be 0. So if I want to know the weight, I need to know the mass. Now the mass is the density multiplied by the volume. So we need to do the volume first. So in order to work out the volume, because this is a square on this end, I've got 25 millimeters multiplied by 25 millimeters. If we do that in meters, it's 25 times 10 to the minus 3 multiplied by itself, so it's squared, multiplied by the whole length of this thing. So it's multiplied by L. Now I don't know L, so I'll just keep L as it is and hope that we can do something with that in a little bit. So that's a volume. So the mass of this thing is the density multiplied by the volume we've worked out. So it's 8.9 times 10 to the 3, which is this density, multiplied by this volume. And if we do that, we can sort out these numbers on our calculator, we get 5.56 lots of L. So therefore the weight, which is equal to mg, is the mass that we've just worked out, multiplied by the acceleration due to gravity of 9.81 meters per second squared. If we do that, we get 54.6 L. So we've still not got rid of this L yet. So in the end, we know that the force upwards must equal the force downwards. Now the force upwards is the magnetic force on this conductor, and they gave us the equation for this in the first part of the question, which is BIL, where B is the magnetic flux density in Tesla, I is our current in amps, and L is the length of the conductor. And that's equal to mg, and we've worked out what mg is because that's this here. So if we substitute that in, B is the thing that we're trying to find out. The 65 is the current which is flowing through this conductor. L is the length, and we don't know that, but that's equal to 54.6 lots of L. So I've got an L on both sides, so now my L's are going to cancel out. So now I've simply got B is 54.6 over 65, which is that part here, which gives me 0.84 Tesla. The final part of this question asks us to draw an arrow to show the direction in which we should apply a magnetic field so that this calculation works. And so we need to just work out the direction of the magnetic field. So to do that, we're going to use Fleming's left-hand rule. So we take our left hand just like we normally do, and the current is going along from left to right. So we place our second finger pointing from the left to the right. We know the force has to be upwards because so it can balance the weight of this bar. And so therefore your first finger points from north to south, and that's going to show you the direction of the magnetic field. So basically we need a magnetic field that's kind of going into the paper. So the easiest way to draw this is to draw it like this. So it's going into the paper like this, and we have to label it M because that's what it asks us to do in the question. So label this arrow M. So that's our arrow, it's going into the paper. So that was question number 2 of the magnetic field homework booklet.